Hi. The purpose of Lab 2 was to model the motion of a falling object using principles from Newton's second law, the fundamental principle. The results were, when analyzing the position versus time data, that the model of the ball including drag and the model of the ball not including drag was similar, with slight variation from the graph produced from Tracker. For my experiment, a ball was dropped from the top of a door and analyzed with Tracker. As I know the height of the door, I use that to calibrate the data for distance. Here's a clip of the ball falling. As you can see here, the ball was then analyzed by Tracker, creating a position in the y direction versus time graph, as you can see right here. Now, when looking at the code, which I will bring up here, which I have enlarged, I have a while loop. While t is less than 0.51, the duration of the clip, W being the force of gravity taken onto the ball, W equals negative ball.m, the mass of the ball, times g being 9.8, the acceleration due to gravity, times j hat, which all combines to give you the force of gravity, the wave force. We also have to take into account the air resistance. Ft equals negative ball times ball.vel, which I have here. Negative b is a value that was calculated by following the lecture video, and there was instructions given on how to get that value in order to calculate the drag force, and that was multiplied by the velocity of the ball, ball.vel. These two values here, W and Fd, represent all the pushes and pulls on the ball while it's being dropped, which is why we sum them to get F net, the total net force. Now we have here the fundamental principle. Ball.vel final velocity equals ball.vel initial velocity plus F net over ball.m, mass of the ball, times delta t, the change in time. And we also have here our next equation used for the position data. Final position equals the initial position plus velocity of the ball times delta t, change in time. Now when looking at the graph used to compare all three, a position versus time graph, as we can see here, it's a comparison of three different plots of data. The blue represents the data from Tracker, the red represents data without the drag force, and the orange represents the data from the model including the drag force. As you can see here, the data is pretty spot on with each other, but there is slight deviation, which could have occurred from inaccurate markings when tracking the ball following downward using Tracker, which is very likely. Now I can show you here when running my VPython code, which I explained earlier. We get what you would expect, which is the ball going down, and you can see here this graph as well. Now, we're going to go on and look at addressing the question. So when examining the velocity versus time in the predicted models, which model will represent the terminal velocity? Well, that would be the model that takes into account drag force. As we know, terminal velocity is when an object falling under the influence of gravity is subject to drag force. It will eventually reach a maximum velocity when the drag force equals the force of gravity. So now we look at what if. What if instead of dropping the ball from rest, I threw the ball down? How would that affect the terminal velocity? Well, the terminal velocity would still be the same. Both balls would eventually reach the terminal velocity if they kept going forever. But the ball being thrown down would just reach the terminal velocity faster. That concludes my video. Thank you for your time.